Hope everyone's doing well. Here's a quick presentation on the superparticular ratios in music. When a string vibrates, it does so with the ends fixed to the instrument. This means that it can only vibrate in certain ways with a certain number of bumps. The more bumps, the higher the pitch and the faster the string vibrates. The frequency of vibration equals the number of bumps times the string's fundamental frequency, or the frequency of vibrations for a single bump. Musicians have different names for the different ratios between pitches. In the traditional music scale, 1 to 2 bumps is called an octave, 2 to 3 bumps is called a perfect fifth, 3 to 4 bumps is a perfect fourth, 4 to 5 bumps is a perfect major third, 5 to 6 is a minor third, some that are not named, and then 8 to 9 bumps is called a whole step. These represent the superparticular ratios in music that define all musical intervals, or the difference in pitch between two sounds, or the length of violin string required to produce first one note and the other. When played, we get nice constant sounds of perfect harmony. Hence, we name these patterns of pitches the harmonic series. We can use harmonics to explain why a bugle playing taps rings out so purely. This is because it only uses notes in a certain series of harmonics. In number theory, Sturmer's theorem states that essentially every Pell equation of the form x squared minus dy squared equals 1 has a fundamental solution. Essentially, all Pell equations have a non-trivial solution, whereby once the fundamental solution is found, all subsequent solutions can be found by multiplying the conjugate solution by itself. One needs to rewrite the Pell equation in terms of a conjugate pair, whereby the conjugate pair represents a norm of square root of d that has multiplicative properties. This can be easily proven. To prove the theorem at large, we use the pigeonhole principle as well as a lemma that bounds the conjugate by a very small number, which follows the idea of having a large, small solution pair. Mathematician Karl Sturmer further devised a procedure that finds all the superparticular ratios that we just talked about in the harmonic series, limited to contain prime factors of 2, 3, and 5. We call this set of prime numbers a 5-limit set, or all the ratios are p-smooth. That is, the set of numbers that can be generated by products of 2, 3, and 5. More generally, for every choice of prime number sets, there's only a finitely many pair of consecutive p-smooth numbers. Sturmer gives a method for finding them all by solving a series of Pell equations generated from the set of p-smooth numbers, and then we test the solutions for smoothness. The superparticular ratios that comprise the harmonic series are embedded in musical tuning. Historically, the art of tuning a piano ran into many difficulties that needed creative solutions because the piano has too many strings, a string for each of the 12 semitones of the musical scale times 7 because there are 7 octaves. If we wanted to tune the piano using perfect harmonics, we could first try using whole steps in the ratio 9 to 8, comparing the 9th harmonic for 1 key with the 8th harmonic 2 keys up. But this only works well for the first 2 keys, for the first few keys. If we do this 6 times, we should arrive at the same note and octave it up with twice the frequency. However, our harmonic tuning method multiplies the frequency by a factor of 9 over 8 6 times, so we end up with 2.027. This is not equal to 2 on the dot. If we try tuning with perfect thirds, we would have to multiply the frequency 543 times, so we still don't get exactly 2. We could try fourths. We would get 1.973. Fifths would get us 2.027. And if we really wanted to try half steps, 16 over 15 to the 12th would also not give us exactly 2. Therefore, we've arrived at the idea that it's mathematically impossible to tune a piano consistently across all keys using perfect, beautiful harmonics. So tuners do not employ rational pure tuning. Instead, all pianos these days employ 12-tone equal tempered tuning, where each successive note is spaced out equally in terms of frequency by the 12th root of 2, since we have to separate the octave into 12 equal intervals, and since musical ratios are multiplicative. But since the 12th root of 2 is an irrational number, something we would never get using the simple superparticle ratios that we've derived from Stormer's method. Since it's an irrational number, it's irrelated. However, the benefit of equal temper tuning is that once we go up 12 keys, we end up exactly at 2, or a perfect octave. 12 through, it does give us a perfect octave interval, a pure octave interval. However, fifths are slightly flat, fourths are slightly sharp, and so on. So we've sacrificed pure rational tuning. However, the benefit is that we can play any song in any key and freely modulate between keys, and everything will be equally and only slightly out of tune, something that we've come to accept, something that our ears do not even pick up with ease.